Okay, Part V, the Dragon's Horde Mastering Complexity and Abstraction. Our final section.
Back to the deep tech.
Yeah, for our final section, we return to the core of computation. We're exploring books that offer profound perspectives on structuring code effectively, managing complexity, and optimizing performance at a deep level.
These are the texts that provide the intellectual tools to move beyond just being a user of systems.
Right.
And become a creator of new abstractions, a true master of the complex machinery that powers advanced AI.
And we're actually revisiting the principles of the Dragon book here. Compilers, Principles, Techniques, and Tools by Aho, Lam, Sethi, and Ullman. Because it so perfectly bridges those foundational principles we discussed earlier with the mastery of complex modern systems, it really feels like a capstone to our technical collection.
I agree. Its enduring value is only magnified in the AI era because it teaches you how to think about and achieve performance optimizations in ways that an AI on its own can't fully grasp. It lacks the deep architectural understanding. Remember, every high-performance AI framework relies on sophisticated compilation techniques internally. Understanding compiler principles means you can identify why an AI model's performance is bottlenecked, often beyond what even an AI-powered profiler tool might tell you. You learn to write code that is JIT-friendly, optimized for just-in-time compilation. You understand concepts like operator fusion, where multiple small operations are combined for efficiency. And you grasp the critical role of intermediate representations, IRs, in modern AI compilers like MLIR.
So that myth we talked about earlier, that it's too theoretical or outdated, that feels especially dangerous in the AI context now, doesn't it? It's clearly not just about handwriting parsers anymore.
No, absolutely not. It's about understanding the fundamental principles that make all these modern runtimes and frameworks work efficiently. An AI engineer who only knows how to tweak prompts or high-level framework settings without this foundational understanding, they'll be at a distinct disadvantage when it comes to deep system-level optimization.
Can you give that TensorRT example again?
Sure. You're optimizing an AI model for inference using NVIDIA's TensorRT. An engineer with Dragon Book principles understands that TensorRT isn't magic. It's building a data flow graph and performing precise optimizations like operator fusion. So, if the compiled model gives incorrect results, they can intelligently debug the compilation process itself. They might suspect issues related to flowing point precision changes during fusion, or maybe an incorrect fusion decision, rather than just treating the compiler as an opaque black box that either worked or didn't.
The debugging insight is key.
It is. You can also apply these principles to build better developer tools yourself, like static analyzers that truly understand code structure and can give much more intelligent feedback than simple pattern matchers.
This expertise uniquely positions you at that critical intersection of AI models, software frameworks, and the underlying hardware, the absolute epicenter of performance.
That's where the magic happens.
You can pursue roles in AI compiler development, deep performance engineering, maybe even hardware accelerator co-design. Roles that are deeply technical, highly valuable, and right at the forefront of innovation today.
And likely to remain so for a long time.
Okay, our next book is the standard textbook for information retrieval. Information Retrieval by Christopher Manning, Prohaka Raghavan, and Henrik Schutze.
Often called IIR, another foundational text.
It covers all those core concepts like Boolean search, vector space models, indexing strategies, evaluation metrics like precision, and recall the science of finding information within large collections of documents.
And this raises a really important question right now. Why is classic information retrieval, IR, still so critical in the age of large language models, LLMs? Haven't LLMs solved search?
Yeah, that's what you hear. Just talk to the AI.
Well, the most powerful and crucially the most reliable AI search systems being built today actually use a technique called Retrieval Augmented Generation, or RA.
Raggy. Okay, what's that?
It's a hybrid approach. First, a classic IR system using principles from this book retrieves a set of potentially relevant documents from a knowledge base, which could be the web or internal company docs. Then, the LLM uses those retrieved documents as context to generate a coherent, informative answer. The IR part finds the facts, the LLM part synthesizes them into language.
Ah, okay. So the LLM doesn't do the searching itself.
Not in real time against specific document sets, generally no. This book provides the foundational knowledge for the critical retrieval part of RAG. The quality of the LLM's final answer depends entirely on the quality and relevance of the documents retrieved by the IR system first.
Garbage in, garbage out, basically.
Exactly. If the retrieval step fails, if it pulls irrelevant documents or misses the key ones, the LLM will either hallucinate an answer based on its generic training data, or it will simply say, I don't know, even if the information exists somewhere. Concepts from the book like term weighting, TF-IDF, vector similarity, cosine similarity, indexing, they are all core to making that retrieval step effective.
So that common myth, LLMs make classic search obsolete, you can just talk to the data now, that fundamentally misunderstands how these powerful generative AI search systems actually work under the hood, doesn't it?
It completely misunderstands it. LLMs don't search effectively in real time across vast, arbitrary data sets. They generate text based on their massive but potentially outdated training data, or they simply lack knowledge of private, proprietary data.
Right.
RAG is the dominant solution for bridging that gap, for grounding LLMs in specific, up-to-date, or private information. And RAG explicitly relies on classic IR principles. This book describes the enabling technology for making LLMs truly useful and trustworthy in real-world search and question-answering applications.
So how does this apply day to day for an engineer working on, say, an AI chatbot?
Okay, imagine you're improving your RAG-based chatbot that keeps giving irrelevant or nonsensical answers. Your first instinct shouldn't be just to blame the LLM.
Debug the retrieval first.
Exactly. You first debug the retrieval component using IR principles. Are the right documents even being pulled for the LLM to use? You might analyze the queries, the indexing, the similarity metrics. Maybe you realize your system relies only on semantic vector search, which is great for conceptual similarity, but bad for specific keywords. Remembering the IIR book, you might implement a hybrid search approach, combining semantic search with traditional keyword search like BM25 for better overall relevance.
Best of both worlds.
Right. For ambiguous user queries, you might apply query expansion techniques, maybe even using the LLM itself to generate alternate phrasings of the user's question to improve the initial search. And critically, you'd use formal evaluation metrics from the book, like precision, recall, and F1 score, to systematically measure whether your changes are actually improving the retrieval quality.
As nearly every company seems to be building AI-powered search or Q&A features now.
It's a huge trend.
There's a massive demand for engineers who understand how to do it well. A deep understanding of information retrieval is the key differentiator.
It really is.
You can build state-of-the-art R8 systems, troubleshoot those complex AI search failures effectively, and lead the way in generative AI search applications. While many engineers can call an LLM API, you, mastering IR principles, can build the robust and reliable retrieval systems that make those LLMs truly powerful and useful.
That's a highly valuable skill right now.
Next up, Elements of Distributed Systems by Andrew Tannenbaum and Martin Van Steen. This provides a comprehensive introduction to the principles and architecture of distributed systems.
Tannenbaum, another giant in the field. His MIX operating system inspired Linux.
Right. The book covers collections of independent computers that need to appear to users as a single coherent system.
And understanding distributed systems is now absolutely fundamental for building any modern scalable software, but especially for large-scale AI systems which are inherently massively distributed.
How so?
Think about training today's huge language models. It requires coordinating potentially thousands of GPUs across a complex network. Serving those models to millions of users requires globally distributed inference infrastructure.
The scale is mind-boggling.
It is. This book gives you the timeless principles for reasoning about these incredibly complex systems. Concepts like transparency, making distributed resources appear local to the user or developer. Communication protocols between nodes. Consistency and replication, absolutely crucial for ensuring model updates or training data are correctly and reliably distributed. And fault tolerance, designing systems to gracefully handle the inevitable partial failures of nodes or networks without the whole thing collapsing.
But again, the common misconception. Cloud platforms make this knowledge unnecessary. The cloud handles all the distributed systems problems for me. Is that truly the case?
That is a dangerously tempting but ultimately false oversimplification. Cloud providers offer incredibly powerful building blocks. Yes, things like managed databases, load balancers, message queues.
But they don't design your system for you.
Exactly. They don't absolve the engineer of the responsibility of architecting a coherent, reliable, and scalable system using those blocks. An AI engineer just deploying models onto multiple cloud virtual machines without understanding distributed systems principles. They'll be completely unable to reason about potential failure modes or data consistency issues or performance bottlenecks that arise from the interactions between the components.
Right.
An AI assistant, lacking this fundamental understanding of the laws of physics for distributed systems, cannot solve these emergent system level problems. This book gives you those laws.
So how would you apply this when designing, say, a scalable AI inference service?
Okay, you need to serve millions of global users.
Mhm.
Guided by Tannenbaum's principles, you'd probably choose a client-server architecture, but with multiple replicas of your AI model running behind a sophisticated load balancer. You'd replicate those services across different geographical regions, maybe using cloud availability zones or regions, for both lower latency to users and better fault tolerance if one region has issues.
As if
You'd have to critically consider the consistency requirements for model updates. Do all users need to see the new model absolutely simultaneously? Strong consistency, which is hard. Or is it acceptable if updates propagate gradually? Eventual consistency. That's a key architectural trade-off. You'd explicitly design for fault tolerance. What happens if a server running your model crashes? The load balancer needs to detect that and redirect traffic seamlessly. And you design for scalability, probably using auto-scaling groups to automatically add or remove model replicas based on current load.
So even if an AI generates the Terraform script or Kubernetes config.
Right. Even if AI helps with the implementation details, this entire design process, making those architectural choices, understanding the trade-offs, requires human judgment grounded in distributed systems principles.
Expertise in distributed systems is clearly one of the most valuable and sought-after skills in tech today, especially in AI.
Without a doubt.
As AI models and the data they consume just keep growing, the complexity of the underlying infrastructure increases exponentially. If you have these skills, you can architect and build truly planet-scale AI systems. You can solve the hardest, most complex production problems, things like debugging race conditions across nodes or handling network partitions gracefully.
The really thorny issues.
And you can command a significant premium in the job market, leading to roles like staff engineer, distributed systems, or principal engineer, AI infrastructure. While AI can write code for one machine pretty well now, designing, building, and managing these global, resilient, scalable systems of machines for modern AI, that remains a deeply human and highly valuable discipline.
It's about orchestrating complexity.
And finally, our last book, Brendan Gregg's System Performance. This is the definitive, practical guide to analyzing and optimizing modern computer systems with a strong focus on Linux, which underlies so much infrastructure.
Gregg is the master of performance analysis tooling and methodology. His work is legendary.
It offers these holistic methodologies and a whole arsenal of tools for performance analysis, digging into everything from the hardware level right up to the operating system kernel and into the applications themselves.
And what's truly compelling here is its direct and immense value in the AI era. AI and ML workloads are among the most performance-intensive applications imaginable. They push every single component of a system, CPU, memory, network, storage, GPUs, to their absolute limits.
Right, they stress everything.
Achieving optimal performance and cost efficiency for AI training and inference. That's a critical business challenge for almost every company using AI today. While CSAPP gave us the theory of computer architecture, Gregg's book gives you the practical, hands-on methodology and the specific tooling for understanding how systems actually perform under load in the real world.
So it's the practice complementing the theory.
Exactly. You learn not just that a memory hierarchy exists, but how to use powerful tools like BPF, the Berkeley packet filter, which allows safe custom tracing in the Linux kernel to actually trace cache misses for a specific AI application running live in production. You can finally answer those tough questions. Why is my expensive GPU sitting idle half the time? Why is network latency so high between my distributed training nodes? Gregg gives you the methods to find out.
Now, a common misconception is that performance analysis is some kind of black art, requiring arcane knowledge. Or, maybe more recently, that new AI-powered observability tools will just solve everything automatically. I imagine it's more nuanced than that.
It absolutely is. While modern observability tools, some using AI, are fantastic for flagging anomalies, hey, CPU utilization spiked. They often don't replace the need for deep human understanding to find the root cause.
They tell you the what, not the why.
Precisely. An AI tool might say CPU utilization is high, but it usually can't tell you why. Is it inefficient application code? Is it contention within the operating system kernel? Is the system spending all its time context switching between processes? Greg's book teaches the methodical approach, like his USE method, to systematically drill down from a high-level symptom to the underlying root cause.
What's the USE method?
It stands for utilization, saturation, and errors. For every key system resource, CPU, memory, disk, network, you check its utilization. How busy is it? Its saturation, is there a queue forming? And if it's generating any errors. It's a systematic way to quickly identify potential bottlenecks. Relying solely on automated tools without this kind of methodical understanding is like seeing a warning light flash on your car dashboard, but having absolutely no idea how an engine actually works. You don't know where to even start looking.
So how would you apply this USE method to diagnosing a slow AI training job? Maybe one where the expensive GPUs seem underutilized.
Okay, great example. You'd apply the USE method systematically. Check GPU utilization, maybe it's low, like 50%. Okay, why? Then you check utilization, saturation, and errors for the other resources. CPU. Maybe the data loading and preprocessing cores are pegged at 100% utilization. Memory. Maybe memory bandwidth is saturated. Disk I/O. Maybe the storage system is saturated, with long queues, high saturation, trying to read the training data.
So the GPUs are starved for data.
Exactly. You've identified an I/O bottleneck as likely the root cause, not the GPUs themselves. Once you understand that, you can then use an AI assistant much more effectively. You can ask a target question like, okay, given an I/O-bound workload on a parallel file system, what are the most efficient file formats and data loading strategies to use in PyTorch to maximize throughput? Now the AI can give you relevant advice.
That makes perfect sense. Diagnosis first, then targeted remedy.
Precisely. Expertise in systems performance analysis is unfortunately rare, but incredibly valuable. In the world of AI, where single training runs can cost millions of dollars, an engineer who can methodically diagnose bottlenecks and shave, say, 20% off that training time, they provide a massive direct return on investment.
Huge ROI.
This skill is fundamentally about diagnosis, investigation, optimization, creative problem-solving activities that are inherently difficult to fully automate. While AI can certainly assist with data collection and maybe suggesting hypotheses, the deep holistic analysis connecting hardware, kernel, and application behavior within a complex production system, that remains a deeply human endeavor.
This positions you as the ultimate performance expert, a high-impact, high-visibility, and incredibly high-value role that will be in demand as long as we continue to push the boundaries of computation.
As long as performance matters, the skill will matter.